Okay, so we are going to discuss now approximate inference, or more specifically variational inference. So what is the whole philosophy of variational inference? As you have seen that we want to approximate my posterior probabilities or any probabilities, right? It could be posterior or anything. I want to estimate my probabilities. But how do I estimate my, uh, I think you saw, we, we saw given Px, we can sample from it. But many times sampling from Px is not computationally viable or feasible even. Then what do we do? Solution is, what is the solution? We approximate Px with uh, a simpler distribution, or basically a distribution easier to sample from. An example could be given. So for example, uh, okay, first let me give you an example that how we can approximate a distribution. Let us say I have a distribution which is like this. This is my, let me call it my P star X, the original distribution. The original distribution. But how will I sample from this distribution? Maybe it is not easy and I don't know how to do it. So what I can do what I can do is, a very simple solution is approximate it with a Gaussian distribution. We call it as Q of X. And this depends on sigma and mu, right? You know, this depends on some mu, some sigma. We call it as Q of X. So this is a Gaussian distribution which I use to approximate my P star of X, and it works very well because uh, if if uh, if it is a good approximation, then in most practical situations I will not need the original P star of X, right? Okay. Now the question is how to find suitable Q of X which approximates P star of X, right? How do I find that distribution? Uh, you may say, okay, we can do variational, no, we can find a parametric Q of X, and then we can find out the values of mu and sigma using maximum likelihood approximation or maximum a posteriori approximation, etc., etc. Right? That is also a very good way. Uh, um, So something in that line we are doing. So okay, how do I tell? Okay, this is a Bayesian approach, which means even my mu and sigma could be uh, random variables, right? In my Gaussian distribution, mu and sigma are deterministic variables, right? But in my Bayesian approach, even mu and sigma will be random variables. So, so we are heading in that direction. So what we are trying to do now is find probability, find probability of sigma and probability of basically given X, or you can see etc. Or it means basically it could be also sigma comma mu comma X, right? It could be anything of this sort. So now what we are going to do, we have to find a Q of X which is close to P star of X. Um, let us say this is a space of PDFs, right? And somewhere here is my P star X. It could be multidimensional. I'm just showing it as 2D just for representation purpose, but it could be multidimensional thing. Now, what I need to do is I need to this is a family of distributions, right? It could be Gaussian distribution, the family of Gaussian distributions. Basically, it means that uh, means space of all PDFs which are Gaussian, for example. Normal. And these are mu can be real, sigma can be real non-negative. Oh, actually, it cannot be zero. It will be that will be a delta function. Okay. So this is what is a family of distributions, right? Similarly, a GMM could be another family of distributions. GMM is another family of distributions. Right? So basically, I have family of distributions, and I want to use that family of distributions to approximate my P star X. So how do I do that? I will be now this family I can determine. This is a kind of my model. Now I want to find the distribution in this family which is closest to P star of X. Which one will that be? This one, right? This one or this one? Which one? Let me call this as Q2. This one is Q1. Which one is closest? The chat window. Q1, yes. Thank you. So Q1 is the closest thing. But how do I find the distance between two distributions? How to find distance in between two distributions? So this distance is a distance between two or two PDFs. How do you find this distance between the two PDFs? Because you want to minimize the distance. Yes, very good answer. By using KL divergence. I can use KL divergence. So this KL divergence is minimum, right? Now, what is KL divergence? KL divergence between two P star and Q is equal to, actually I can write Q first for a reason. which is you do some integration. Let's say it is a continuous variable, x is a continuous variable, qx log of qx upon p star x dx. X can be a vector, then it will be a vector integral over all possible x. That is my KL divergence, right? Uh, so this quantity I need to minimize. Now see, if I want to minimize this, how will I minimize this? I will say minimize with respect to a function q. Right? Q is a function of different parameters or different random variables, because parameters are also random variables in this case. So this whole thing becomes a functional because it's a function of functions. KL divergence is a function of a function or functions. This is a function of function. So it's called a functional. Now, just like in normal calculus, we modify our, let's say I have a f of x. So I do slight variations in x plus dx, and then I get fx plus dx times f dash x, right? But if this is called the normal calculus, but what happens in functional derivative, we have the scale divergence of q and p star. Now if I do slight variation in q, then I get KL divergence, this thing, plus some derivative term. This is the functional derivative. So there are different methods to compute functional derivatives. So today we'll be studying some ways to minimize my KL divergence. So what we are doing here is we are doing, okay, I will show you what we can do. Okay, now one advantage of using KL divergence, one advantage of using KL divergence as the distance metric. So I'm just, so many times what happens, calculating or many times calculating p star x is not directly feasible. This is equal to some normalization constant, which is intractable, which means it is very difficult to compute. So in those cases, we only know this. I will give you one example. One example, a very common example is icing model. It's a very popular toy model. So what is an icing model? Icing model is basically a lattice. Let me draw a 4x4 matrix, 4x4 lattice. Okay. Now, what happens is my terms can be either +1 or -1, right? Let's say this is my yi. So my each yi can be either +1 or -1, right? Imagine this is like a magnet that in the, for example, magnet. In my magnet, my magnetic domains could either point upwards or downwards. It's a discrete kind of magnetic domains. And if my domains are both aligned in the same direction, then let us say I have um, less energy, which means at a lower temperature, all my domains are aligned in the same direction. At low temperature. At high temperature, they are all random. At high temp means all random means all in different directions at high temperature, right? This is a ferromagnet. This is called a ferromagnet. Okay, and how do we represent this magnet? I say the energy of this magnet is given by a term. Energy of this magnet Y is given by basically some beta, or you can call capital J, means people use different notation. Some people use beta, some people use capital J. Summation over all the neighbors, I comma j. So this is, let's say if this is my I, this is my j. So whenever they are neighbors, these are neighbors, I comma j, summation over all neighbors, yi times yj, right? Plus, okay, let us first try to understand only this much. So this is a ferromagnet. For a ferromagnet, my beta is, I think, greater, no, it's less than 0. Beta is less than 0. Am I doing it correctly? No. Okay, it's minus beta. Okay, so this is my energy, and my beta is greater than 0 for ferromagnet. What does that mean? This means, let us say my beta is a large value. Say beta is very, very large value. This implies if all yi are 1, then my energy will be how much? Minus beta times, which means minus large value. All y's are equal to 1. So everything is 1. So this will be a large number, some capital N. Let us, there are n number of neighbors. Then capital N, some large value. Right? Actually, this beta is inversely proportional to temperature, which means if I have a low temperature, at low temperature, my beta is very large. So beta is inversely proportional to temperature. This means at a low temperature, my beta is very large. So this means, therefore, all spins are aligned in same direction. But now imagine all the yi's are, if all the yi's are -1, then also same, E of y is minus beta times n, right? -1 into -1 is again +1. So this means that again, all my energies are, my energy is still the minimum. So basically what it means, at low temperature, I can have all the spins aligned in the same direction, either upwards or downwards, right? So this is the Ising model. But if you heat it up at a higher temperature, then depending on the temperature, you will have different distributions. Let's say at certain temperature, you will get some spins get flipped, but at a very high temperature, almost all spins are flipped. And at a very, very high temperature, the distribution will be exactly up, down, up, down, up, down, up, down, right? Because this will have the maximum energy. E of phi will be, so this, if this is this way, well, let's say this is 4 cross 4 only. Then my E of y is beta times plus 1. So beta times n. Very high energy. The energy of this lattice is very large. So at a higher temperature, I prefer configurations which have higher energy. Right? At higher temperature, my beta is very, very close to 0, very small. Then my uh, energy configuration is, this configuration is preferred. So now you see what is the PDF at a given temperature or at a given beta. So my probability of y, how do I find out? So this comes from Boltzmann distribution. So there Gibbs distribution or Boltzmann distribution. It says E of minus Ey divided by Z, the normalization factor. Or it's also called a partition function. Just a confusing name. Partition function or normalization factor. So see, this is one practical example where you cannot compute P of y exactly. You can only compute the numerator term, and this constant z is constant with respect to y, right? Whatever are the values of y, z is constant with respect to y. So this is one example where you cannot compute py exactly. You can only compute the numerator, but the denominator term, which is independent of y, is intractable, right? So this is so that is why, and this is not just one example. There are so many examples which are intractable in nature, like even your images. So estimating p of y is very difficult for images also. Um, so that is why KL divergence. Let us look at KL divergence. Q uh, divergence with P star. Now let us say if I approximate my P star of y with some P hat of y upon Z, right? Where P hat of y depends on y, Z is independent of y. Then if I want to do KL divergence of some Q of y with P star of y, then this becomes integration of Qy log of Qy upon P star of y, which is basically P hat of y upon Z. And then here you have D of y, right? Now you can say this is equal to Q of y log of Q of y upon P hat of y. These terms are known, so no problem. And this term can be written as, see, this goes to the top, and you can write this as plus log of Z and D of y. Right? And you can separate them up. You can say this is Q of y log of Q of y upon P of y, D of y, this term, plus another term, which is basically log of Z, which is independent of y. Then this is simply Q of y, D of y. And you know this term is 1, right? Integration of Qy over all y is simply 1. So this term is simply a constant term. This is P hat, right? So basically, you can minimize this with respect to Qy. And this term is independent. Right. So you can use KL divergence even in such cases. And uh, in the next class, we'll see how do you derive an approximation of Ising model. If I ask you to sample configurations, this lattices from P of I, given this PDF, it is so difficult, right? Because you cannot sample them directly. So you have to use some approximation to be able to sample from this distribution. And that is what we will be discussing in next class. But now we are going in that direction. So let's discuss this method of mean field approximation. Mm. So mean field approximation is a kind of variational inference. So what you do is, first of all, you select a family of distributions Q. Which is basically easy to sample from. Now, this Q is special Q, which is what do you say? Factorized distribution. So basically, you say my Q is a family of all the Q such that Q of the vector Z is equal to Q of Zi product over all I. So this is your mean field approximation. This is so you are choosing factorized distribution and you are assuming them as independent. And then of course, you know that you find uh, you find your best approximation by using tail divergence QZ P of Z. You minimize it with respect to Q, which belongs to this family Q, right? Okay. So this Q star is the best approximation of P star. So this is mean field approximation. So this basically you are estimating or approximating your family P star with the help of, you're approximating your P star with a family of Q, which is basically assuming that all the latent variables or all the Z variables are independent. So an example could be given here. So what is your example? Let us say, take a Gaussian distribution. Let us say my P star of Z is basically Z1, Z2. Or you can also write it as P of Z1, comma Z2. Let us say this is equal to a normal distribution. You can say okay, Z given vector mu, comma, some sigma, right? So how many latent variables are there? How many, hidden parameters are there in this distribution? Can you write on the chat window? In this distribution, how many variables are there? How many tunable parameters to determine my distribution? How many parameters are there? 5. Okay, let us see. So mu can have two values. It has got mu1, mu2, like two variables. And this has got how many? Four, right? Sigma is a 2 cross 2 matrix.
Sir,
And
but it is symmetric, no, sir?
yes, very good. It has got four values. So this is a matrix, but it is symmetric. This is your expectation, or you can say variance of z1 comma z2. Sorry, z1 comma z1, and this is the variance of z1 comma z2. This is the variance of z2 comma z1, and this is the variance of z2 comma z2. So these two things are same. So it is 4 minus 1. So it is 3. Total 5. 5 unknown parameters are there. Okay. Now, if we want to use mean field approximation, then I will say my P star of Z is equal to Q of Z1 into Q of Z2. And I can again assume that my each Q is also normal distribution. So my Q of any Z is basically normal Z comma mu comma given mu comma sigma. Now, how many latent variables are there? How many latent variables are there here? How many latent variables are there now? So this is actually this I can write as Q1 simply. Q1, Q2. My each Qi Vi is simply. So this means this is mu I. So there are, this has got 2, and into 2. Total 4 parameters are there, right? So I have reduced my number of parameters. So if you take more number of z's here, then the reduction will be even more significant, because this is increasing linearly, this is increasing exponentially. Exponentially, right? Yeah, exponentially. So exponential increase versus linear increase. No, not exponentially. It is square, not linear, but square, right? Okay, so in this way I have reduced my number of parameters. And geometrically, how does it look like? Geometrically, it is something like this. You have got a Gaussian distribution of two variables. It is something like this, right? This is your mean, mu vector, right? And then this is your sigma matrix, covariance matrix. But if you are approximating it with this mean field approximation, then what you get is basically, it will be like this. So your mean may be still the same. Mean will be mu1, mu2. And along here it will be sigma 1. Along here it will be sigma 2. And there is no diagonal term, so your Gaussian distribution is not tilted, but it is aligned along the axes. This is called my mean field approximation. Now, I can use this mean field approximation on basically any kind of distribution, but we will be looking at this mean field approximation in the context of Ising model, and more generally in the case of uh, lattice models, such lattice models. We'll be seeing mean field approximation in the case of lattice models. So, anyways, so I think it since it is almost the time, we can stop here, and in the next class we can discuss about one example of deriving mean field approximation. Okay, I can stop here. Any questions at this moment?
Sir, I have a doubt about project.